There is something quietly astonishing about the night sky. When you look up on a clear evening, you see thousands of points of light scattered across darkness. Each one is a sun, burning across distances so vast that their light has traveled for years, sometimes centuries, just to reach your eyes. And yet, despite this immensity, what you are seeing represents only the tiniest fraction of what exists. The observable universe extends in all directions for approximately 46.5 billion light-years from where you stand. This creates a sphere roughly 93 billion light-years in diameter, containing everything that light has had time to reach us since the beginning of cosmic time. Within this sphere exist an estimated 2 trillion galaxies, each containing hundreds of billions of stars. The numbers become almost meaningless at this scale, and yet this observable region, as incomprehensibly large as it is, represents just one small bubble in something far more vast. Scientists use the term multiverse to describe the possibility that our observable universe might be just one among many, perhaps infinitely many, separate regions of space and time. This is not science fiction or wishful thinking. The multiverse emerges naturally from several well-established areas of modern physics. It arises from quantum mechanics, the most precisely tested theory in all of science. It emerges from cosmological inflation, a framework that explains fundamental features of our universe that we can observe and measure. It appears in string theory, humanity's most ambitious attempt to unite gravity with the other forces of nature. Tonight, we are going to explore these ideas together. We will move slowly through the science, pausing to let each concept settle into place. There will be no rushing, no urgency. The multiverse, if it exists, has been there long before you were born and will remain long after you have gone. It requires nothing from you. It simply is, existing in its own vast and quiet way, indifferent to observation, persistent across scales of time and space that dwarf human comprehension. You can listen to this however feels right. You might be lying in bed, letting the words wash over you as you drift towards sleep. You might be sitting in a quiet room, allowing yourself to imagine spaces beyond imagining. You might return to this multiple times, each time noticing something different, each time letting the scale of it settle more deeply into your awareness. There is no wrong way to experience this. The journey ahead will take us through 11 dimensions folded smaller than atoms. We will explore universes spawning endlessly in an eternal cascade of creation. We will contemplate quantum branches where every possible outcome of every event manifests in some region of reality. We will consider the precise calibration of physical constants that allows matter to form structures, stars to burn, and life to emerge. And we will sit with the profound strangeness that this might all be happening right now in ways and places forever beyond our ability to directly observe. The multiverse is not a place you can visit or a thing you can touch. It is a framework for understanding why our universe has the particular properties it does. It is a way of making sense of observations that, when taken seriously, seem to demand that what we see cannot be all there is. And perhaps most importantly, for our purposes tonight, it offers a perspective that can be oddly comforting. Your problems, your worries, your restless thoughts, they exist in this one small branch of possibility, in this one pocket of space and time, in this one configuration of matter that happens to include you. Somewhere, in the vast landscape of the multiverse, if the theories are correct, there might be versions of reality that are calmer, quieter, more peaceful. And somewhere, there are versions that are more chaotic, more unstable, less hospitable. We happen to find ourselves here in a universe that permits stars to form, planets to orbit, and consciousness to emerge and wonder about its own origins. Let that settle for a moment. Take a slow breath. The universe is not asking anything of you right now. It simply continues, vast and patient, following the mathematical rules that govern its behavior. Gravity pulls, light travels, particles interact, and somewhere in all of this, you exist, aware and present, able to contemplate these immense questions from your small, temporary perspective. We will begin our exploration with the most fundamental question about the multiverse, the question that underlies everything else we will discuss. What exactly do we mean when we use this word? What are we really talking about when we suggest that our universe might be just one among many? The word multiverse can refer to several distinct concepts, each arising from different areas of physics. This can be confusing at first because people sometimes use the same word to describe quite different ideas. One version of the multiverse has to do with quantum mechanics and the way reality might branch with every measurement or interaction. Another version emerges from cosmology and the theory that space has been expanding forever, creating an endless succession of bubble universes. A third version involves extra dimensions, spaces curled up so small we cannot detect them, each potentially harboring different physics. The physicist Max Tegmark proposed a useful framework for organizing these ideas, arranging different types of multiverse into 4 levels, each more speculative than the last. At the first level, we simply have infinite space. If space goes on forever in all directions, and if the distribution of matter follows certain patterns we observe in our local region, then eventually, given enough distance, every possible arrangement of particles must repeat. At the second level, we have eternal inflation, a process where different regions of space stop inflating at different times, creating bubbles with potentially different physical laws. At the third level, we have the many worlds interpretation of quantum mechanics, where the universe constantly branches into parallel versions of itself. And at the fourth level, Tegmark speculates about a mathematical multiverse where every logically consistent mathematical structure exists as a physical reality. Not all of these ideas have equal scientific support. Not all physicists accept them. Some, like physicist John Horgan, have criticized multiverse theories as pseudoscience, arguing that they cannot be tested and therefore fall outside the proper domain of physics. Others, like Sean Carroll, argue that the multiverse is an inevitable consequence of theories we have already tested and verified. The debate continues, and that is part of what makes this subject fascinating. We are at the edge of what science can currently tell us about reality, but tonight, we are not here to resolve scientific debates. We are here to contemplate possibilities, to let our minds expand to consider scales and concepts that are genuinely difficult to grasp. We are here to find a kind of peace in contemplating how vast and strange reality might actually be. Let us start with something concrete, something measurable, something we know with considerable certainty. Let us start with the observable universe itself, the region of space from which light has had time to reach us. The universe is approximately 13.8 billion years old. This age comes from multiple independent lines of evidence, including measurements of the cosmic microwave background radiation, observations of distant supernovae, and calculations of the expansion rate of space. The precision of this measurement is remarkable. Scientists can state the age to within about 21 million years, an uncertainty of less than 0.2%. Given this age, you might expect that the observable universe would extend 13.8 billion light-years in all directions for a total diameter of 27.6 billion light-years. Light travels at a fixed speed, roughly 300,000 kilometers per second, so in 13.8 billion years, light should travel 13.8 billion light-years. But the universe is not that simple. Space itself has been expanding throughout the entire history of the universe. When light left a distant galaxy billions of years ago and began traveling toward us, space between that galaxy and our location was also expanding, stretching out as the photons journeyed across the cosmos. This means that the galaxy which emitted that light billions of years ago is now much farther away than the light travel time would suggest. The current distance to the edge of the observable universe is approximately 46.5 billion light-years. This is the radius measured from Earth in any direction. The diameter is therefore about 93 billion light-years. These are proper distances measured at the present moment, taking into account all the expansion that has occurred. Let that number rest in your mind for a moment. 93 billion light-years. A single light-year is already an incomprehensible distance, roughly 9.5 trillion kilometers. Multiply that by 93 billion. The observable universe is a sphere 93 billion light-years across, filled with approximately 2 trillion galaxies, each containing hundreds of billions of stars. And this observable region is almost certainly just a small part of the total universe. Space does not end at the boundary of what we can see. The cosmic microwave background, the oldest light we can detect, comes from a time when the universe was only 380,000 years old. At that time, the universe was filled with hot, dense plasma that gradually cooled enough for atoms to form and for light to travel freely. This created a kind of opaque boundary in time. We cannot see further back than this using light, not because nothing existed before, but because the universe was opaque to radiation before atoms formed. Beyond the edge of the observable universe, space almost certainly continues. Current observations suggest that the universe is spatially flat or very close to flat. In cosmology, a flat universe is one where parallel lines remain parallel forever, following the rules of Euclidean geometry that you learned in school. A flat universe that is also infinite would extend forever in all directions, with no edge, no boundary, no center in any meaningful sense. If the universe is infinite, then our observable region is just one bubble among infinitely many such bubbles, each centered on a different location, each containing a different set of galaxies and structures, but all following the same physical laws. Every location in an infinite universe has its own observable region, its own sphere of visibility, its own horizon beyond which information cannot yet have arrived. This is sometimes called a Level 1 multiverse, the simplest and least controversial type of multiverse. It requires no new physics, no speculative theories. It only requires that space is infinite and that matter is distributed in a roughly uniform way on large enough scales. Both of these assumptions are consistent with current observations. Let us turn now to a different kind of multiverse, one that does not require infinite space, but instead emerges from the mathematics of quantum mechanics. This is perhaps the most famous version of the multiverse idea, and also one of the most philosophically challenging. Quantum mechanics is the theory that describes how matter behaves at the smallest scales, the scales of atoms and subatomic particles. It has been tested with extraordinary precision for nearly a century, and every prediction it makes about the behavior of particles and fields has been confirmed by experiment. It is the most successful scientific theory ever developed in terms of predictive accuracy. And yet, it contains something deeply puzzling. In quantum mechanics, particles do not have definite properties until they are measured. Before measurement, a particle exists in what is called a superposition, a mathematical combination of all possible states it could be in. An electron, for example, does not have a definite position before you measure it. Instead, the quantum equations describe a probability distribution, a mathematical function that tells you where the electron might be found if you look. When you perform a measurement, the superposition appears to collapse. The electron is suddenly in one definite location. The probability distribution, which previously described many possibilities, suddenly describes only one. This transition from many potential outcomes to one actual outcome is called the measurement problem, and it has puzzled physicists since the early days of quantum theory. One interpretation, often called the Copenhagen interpretation, says that the act of measurement somehow causes the superposition to collapse into a single reality. This raises immediate questions. What counts as a measurement? Does it require a conscious observer? How does the universe know when to collapse the wave function and when to leave it in superposition? In 1957, a young physicist named Hugh Everett proposed a radically different answer. What if the wave function never collapses? What if the reason we only see one outcome is not because the other possibilities disappear, but because reality splits into branches, one for each possible outcome? Everett called this the relative state formulation of quantum mechanics. Later, physicist Bryce DeWitt popularized it under the name many worlds interpretation. The idea is simple to state, but difficult to fully grasp. When a quantum measurement occurs, or more generally, when a quantum system interacts with its environment in a way that could produce different outcomes, the universe branches. All possible outcomes occur, but in separate, non-communicating branches of reality. From inside any one branch, you see only one outcome. If you measure the position of an electron and find it here rather than there, it is not because the other possibility vanished. It is because the version of you in this branch sees the electron here, while another version of you in another branch sees it there. Both versions are real. Both are equally actual. They simply cannot communicate or interact with each other once the branching has occurred. This interpretation eliminates the collapse of the wave function. There is no special role for measurement, no mysterious transition from quantum to classical. The Schrödinger equation, the fundamental equation of quantum mechanics, governs everything deterministically. The entire universe is described by a single, evolving wave function that never collapses. What appears as randomness from inside any particular branch is actually just ignorance about which branch you are in. The many worlds interpretation is deeply strange. It suggests that every time any quantum interaction occurs anywhere in the universe, reality branches. Given that quantum interactions are happening constantly, everywhere, at every scale, this means reality is branching trillions upon trillions of times per second. Each branch is real. Each contains conscious observers who perceive themselves as living in a single, definite universe. But from a global perspective, there is only one wave function, evolving deterministically, containing all possible histories. This raises profound questions about personal identity and probability. If you are about to undergo a quantum measurement with two equally likely outcomes, the many worlds interpretation says that both outcomes will occur. There will be two future versions of you, one who observes each outcome. From your current perspective, which one will you become? The answer, according to the interpretation, is that this question is meaningless. You will become both. Each future version will remember being you and will feel continuous with your present experience. Some philosophers and physicists find this deeply unsettling. Others find it elegant and satisfying. The many worlds interpretation requires no collapse, no special role for consciousness, no mysterious process that happens during measurement. It takes the mathematics of quantum mechanics completely seriously, accepting all of its implications, even when those implications are counterintuitive. The interpretation has gained considerable traction in recent decades, particularly among physicists working on quantum computing and quantum information. In quantum computing, the ability of quantum systems to exist in superposition is harnessed to perform certain calculations much more efficiently than classical computers can. David Deutsch, one of the pioneers of quantum computing, has argued that quantum computers provide evidence for the many worlds interpretation. Where else, he asks, could the computational power come from, if not from parallel versions of the quantum computer existing in other branches of reality, all working simultaneously on the same problem? Critics respond that this is not evidence for many worlds, but simply a restatement of what quantum mechanics predicts, which all interpretations must agree on. The disagreement is about what is really happening beneath the mathematical formalism, and such questions may not be answerable through experiment alone. One crucial development in understanding quantum mechanics has been the study of decoherence. Decoherence is a process by which quantum systems interact with their environment, causing superpositions to effectively become classical probability distributions from the perspective of any observer within the system. This happens extremely quickly for macroscopic objects, which is why you never see large objects in noticeable superpositions. An atom can be in a superposition of being here and there simultaneously, but a cat, composed of trillions upon trillions of atoms, each interacting with countless other atoms and with the surrounding environment, decoheres almost instantly. The quantum branches corresponding to different positions of the cat become entangled with the environment in ways that make interference between branches impossible to observe. Decoherence does not solve the measurement problem by itself. It does not tell us whether the wave function actually collapses or whether branches are genuinely created. But it does explain why the quantum world appears classical to us. It explains why we never directly observe macroscopic superpositions, even though quantum mechanics allows them mathematically. The world appears classical because decoherence has entangled quantum information with the environment in ways that are practically irreversible. In the many worlds interpretation, decoherence is the process that creates branches. When a quantum system decoheres, information about different outcomes becomes encoded in different parts of the environment. These different parts cannot interfere with each other, so they evolve independently, effectively becoming separate branches of reality. The number of branches in a many worlds universe is difficult to conceptualize. It is not infinite despite common misunderstandings. The wave function is a single mathematical object. The branches are aspects of this object, not separate universes in the way bubble universes in an inflationary multiverse might be. They share the same underlying quantum state, just divided into non-communicating portions. What does this mean for you, lying here, considering these ideas? It means that if the many worlds interpretation is correct, you are constantly branching. With every breath you take, every photon that enters your eye, every neuron that fires in your brain, quantum events occur that have multiple possible outcomes. In some branches, those outcomes play out one way. In other branches, they play out differently. And yet you experience only one continuous thread of consciousness, one sequence of events, one history. The other branches are not accessible to you. You cannot travel to them or communicate with them. They exist, in a sense, but exist beyond any horizon you could ever cross. They are as unreachable as the regions of space beyond the observable universe, separated from you not by distance, but by decoherence, by the irreversible entanglement of quantum information with the environment. There is something peaceful in this, perhaps. The choices you make, the outcomes you experience, feel significant and real because they are significant and real within your branch. But in the larger structure of the quantum multiverse, all possibilities play out. Nothing is truly lost. Every potential future exists somewhere in the branching tree of reality. Take a moment to let this settle. Breathe slowly. You exist in one branch of an inconceivably vast quantum tree. That branch is real. Your experience is valid. And somewhere, in the mathematical structure that underlies everything, all other possibilities exist as well, equally real, equally valid, forever separated from your awareness by the irreversible march of decoherence. The multiverse emerges from quantum mechanics. It also emerges from cosmology, from our understanding of how the universe began and how it has evolved over cosmic time. This cosmological multiverse is different in character from the quantum multiverse, though some physicists believe they may ultimately be related. To understand the cosmological multiverse, we need to understand inflation, one of the most important ideas in modern cosmology. Inflation is a theory about what happened in the first tiny fraction of a second after the Big Bang, a period of exponentially rapid expansion that solved several puzzles about the structure and properties of the universe we observe today. Before inflation was proposed, cosmologists faced several problems. One was called the horizon problem. When we look at the cosmic microwave background radiation, we see that it has almost exactly the same temperature in all directions, to within about 1 part in 100,000. This uniformity is puzzling because regions on opposite sides of the sky have never been in contact with each other, according to standard Big Bang cosmology. They are separated by distances too great for light to have traveled between them in the age of the universe. So how did they come to have the same temperature? Another problem was the flatness problem. Space can have curvature, bending positively like the surface of a sphere or negatively like a saddle. Observations show that our universe is extremely flat, very close to the boundary between these different geometries. But in standard Big Bang cosmology, flatness is unstable. Any small deviation from perfect flatness should be amplified rapidly as the universe expands. The fact that we observe the universe to be so close to flat suggests that it must have been extraordinarily flat in the early moments, tuned to an absurd precision. This seems unlikely without some explanation. In 1979, physicist Alan Guth proposed inflation as a solution to these problems. He suggested that in the very early universe, a fraction of a second after the Big Bang, space underwent a period of exponentially rapid expansion, doubling in size many times over in an incredibly brief interval. This expansion was driven by a special kind of energy, vacuum energy, associated with a field called the inflaton field. During inflation, space expanded faster than the speed of light. This does not violate relativity, because it is space itself that is expanding, not objects moving through space. The expansion stretched quantum fluctuations to enormous scales, seeding the formation of galaxies and large-scale structures we see today. It also solved the horizon problem by bringing distant regions into contact before inflation began, allowing them to equilibrate to the same temperature. And it solved the flatness problem by making space exponentially flat, driving any initial curvature down to undetectable levels. Inflation was a theoretical triumph, and over subsequent decades, observations have provided strong support for the theory. The cosmic microwave background shows exactly the pattern of fluctuations that inflation predicts. The large-scale distribution of galaxies matches inflation's predictions. Multiple independent lines of evidence have converged to make inflation the standard picture of the early universe. But inflation has an unexpected consequence. Once inflation starts, it is very difficult to make it stop everywhere at once. The inflaton field that drives inflation is subject to quantum fluctuations. In some regions of space, the field might decay, ending inflation and allowing a normal, slowly expanding universe to form. But in other regions, quantum fluctuations might drive the field back up, causing those regions to continue inflating. This leads to a picture called eternal inflation. In eternal inflation, space is always inflating somewhere. Even though inflation ends in some regions, creating bubble universes like ours, other regions continue to inflate, and within those inflating regions, more bubbles form. The process never stops. It is eternal into the future and, according to some versions, may have no beginning in the past. Each bubble that forms is a separate universe, causally disconnected from other bubbles. Light and information cannot travel between bubbles because the inflating space between them is expanding too rapidly. Each bubble has its own Big Bang, its own cooling and structure formation, its own galaxies and stars. And if string theory is correct, each bubble might also have different effective physical laws, different values for the fundamental constants, depending on how the extra dimensions of string theory are configured in that particular bubble. This is called the string theory landscape, and it involves an enormous number of possible configurations. String theory, in its most ambitious form, attempts to unify all forces of nature, including gravity, by proposing that the fundamental constituents of reality are not particles but tiny, vibrating strings. These strings exist in a space-time with 10 or 11 dimensions, depending on the specific version of the theory. To explain why we only observe 4 dimensions, 3 of space and 1 of time, string theory proposes that the extra dimensions are compactified, curled up into tiny spaces too small to be directly observed. The way these extra dimensions are curled up determines the effective physics of the 4-dimensional universe we experience. Different configurations, called caliber-Yau manifolds in the technical literature, correspond to different sets of physical laws and constants. The number of possible Calabi-Yau manifolds is enormous, estimated to be on the order of 10 to the power of 500 or more. Each one corresponds to a different possible universe with different physics. In the context of eternal inflation, different bubbles might settle into different configurations, creating a vast landscape of possible universes, each with its own laws, its own constants, its own structures. Our universe in this picture is just one bubble among inconceivably many. It happens to have the particular configuration that allows stars to form, planets to orbit, chemistry to become complex enough to support life. Other bubbles might have stronger or weaker gravity, different values for the electric charge, different masses for electrons and quarks. Most of these configurations would be sterile, unable to produce the kinds of complexity we see around us. But in an eternally inflating multiverse, all possibilities are realized somewhere. The eternal inflation multiverse is vast beyond comprehension. Each bubble is itself vast, potentially infinite if space is flat. And there are infinitely many bubbles forming constantly in the eternally inflating space between them. The full structure is fractal-like, with inflation occurring at different times in different places, creating a hierarchy of nested structures that extends forever in space and time. This is the cosmos as modern cosmology describes it, if eternal inflation is correct. Not a single universe with one Big Bang and one history, but an endless, ever-growing structure, a multiverse that contains every possibility, every configuration, every potential form that matter and energy can take, given enough space and time. And somewhere in all of this, there is a small bubble where space has stopped inflating, where matter has cooled and clumped into galaxies, where one particular star has a planet with liquid water and complex chemistry, where beings have evolved who can ask questions about where they came from and what else might be out there. That is here, that is us, one small branch of an infinitely large tree. Let yourself rest with that thought. You are part of something incomprehensibly vast. Your existence, your awareness, your moment of consciousness occurs in one tiny bubble of the multiverse, but that bubble is no less real for being tiny. It is your home. It is the stage on which your life unfolds. And beyond it, the multiverse continues, indifferent and eternal, following the impersonal laws of physics, creating and destroying universes with no purpose, no intention, no awareness of its own grandeur. Breathe. Be present. The universe does not need you to understand it. It unfolds whether you are watching or not. But here you are, watching, aware, a brief flicker of consciousness in the vast dark, pondering the nature of reality from your temporary perch in space and time. Before we venture further into speculative territory, let us pause and consider what we know with confidence about the universe we can actually observe. This observable region is not speculative. It is measured, mapped, and understood in considerable detail. And yet, even this known universe is so vast that contemplating it can induce a kind of peaceful vertigo. The observable universe has a radius of approximately 46.5 billion light-years. This number comes from careful calculations that account for the expansion of space over cosmic time. When we observe a galaxy that emitted light 13 billion years ago, that galaxy is now much farther away than 13 billion light-years, because space has been expanding the entire time the light was traveling toward us. Within this sphere of observability exist approximately 2 trillion galaxies. This estimate comes from deep field observations, where telescopes point at tiny patches of apparently empty sky and collect light for days or weeks, revealing thousands of galaxies in regions that appear dark to the naked eye. By counting galaxies in these deep fields and extrapolating to the full sky, astronomers estimate the total number of galaxies in the observable universe. Each galaxy contains, on average, hundreds of billions of stars. Some galaxies are small, dwarf galaxies with only a few billion stars. Others are massive elliptical galaxies with trillions of stars. Our own Milky Way galaxy contains between 200 billion and 400 billion stars, a typical number for a spiral galaxy of its size. If we multiply 2 trillion galaxies by an average of 100 billion stars per galaxy, we get approximately 200 billion trillion stars in the observable universe. This is written as 2 times 10 to the power of 23 or 200 sextillion. Each one of those stars is a nuclear furnace, fusing hydrogen into helium, releasing energy that has traveled, in many cases, for millions or billions of years before reaching us. Many of these stars have planets. Recent surveys by the Kepler Space Telescope and other observatories suggest that most stars host planetary systems. Estimates vary, but a conservative estimate is that there are more planets than stars in the universe. Some stars have one planet, others have many. The diversity of planetary systems is staggering. Hot Jupiters orbit close to their stars, completing full orbits in days. Super-Earths, planets larger than Earth but smaller than Neptune, are common. Icy worlds orbit in the cold outer regions of their systems. Among these countless planets, some fraction will be rocky worlds orbiting in the habitable zone of their stars, the region where temperatures allow liquid water to exist on the surface. Water is essential for life, as we know it, though we cannot rule out the possibility of life based on different chemistry. Estimates suggest there might be billions of potentially habitable worlds in our galaxy alone. Multiply that by 2 trillion galaxies, and the number of places where life might exist becomes almost incomprehensibly large. But even this abundance of worlds is contained within a region that represents only a tiny fraction of the total universe, if the universe is infinite. The observable universe is defined by a horizon, a boundary beyond which light has not had time to reach us. This boundary is not a physical edge, but a limit of observation. Space continues beyond it, following the same laws, containing the same types of structures. As the universe ages, the observable region grows. Light from more distant galaxies reaches us. The horizon expands, revealing structures that were previously beyond our view. But at the same time, the accelerating expansion of the universe is pushing distant galaxies away from us faster than light can travel. Eventually, galaxies that are currently visible will cross a boundary called the cosmic event horizon. Once they cross this boundary, light they emit will never reach us, no matter how long we wait. They will fade from view, disappearing not because they have been destroyed, but because the space between us and them is expanding faster than light can cross it. This means the observable universe is not just a region defined by how far light has traveled since the beginning, it is also limited by acceleration. There are galaxies we can see now whose current light will never reach us. We are seeing them as they were in the past, and we will continue to see older and older images of them, but we will never see them as they are now or as they will be in the future. The universe is patient. It expands steadily, indifferent to observation. Galaxies drift apart, space stretches. And in all of this immensity, in all of this duration, you exist for a brief moment, aware and conscious, able to contemplate these vast scales from your small perspective. Within the observable universe, matter is not distributed randomly, but is organized into a cosmic web. Galaxies cluster together into groups and clusters, which in turn are organized into superclusters connected by filaments of dark matter and gas. Between these filaments are vast voids, regions of space largely empty of galaxies, where only a few isolated structures exist. This cosmic web is the result of gravitational collapse acting on the tiny density fluctuations created during inflation. The largest structures in the universe are these filaments and walls of galaxies, stretching across hundreds of millions of light years. The Great Wall, discovered in the 1980s, is a sheet of galaxies stretching more than 500 million light-years across. The Sloan Great Wall is even larger, stretching over 1 billion light-years. These structures are so large that light takes hundreds of millions of years to cross them, and yet they are still just features within our observable region, dwarfed by the size of the universe as a whole. Between the galaxies lies mostly empty space, but not entirely empty. There is gas, primarily hydrogen and helium, left over from the Big Bang. There are high-energy particles, cosmic rays, traveling at nearly the speed of light. There is radiation, photons from the cosmic microwave background, cooled by expansion to just a few degrees above absolute zero, filling all of space uniformly. And there is dark matter, an unknown form of matter that does not emit or absorb light, but reveals itself through its gravitational effects on visible matter. Dark matter makes up approximately 85% of the matter in the universe. We do not know what it is. It is not made of atoms. It does not interact with light. But we know it is there because galaxies rotate faster than they should if only visible matter were present. Galaxy clusters hold together more tightly than visible matter alone could explain. The cosmic web structure requires dark matter to form. Something unseen, something dark, is out there in vast quantities, shaping the structure of the universe in ways we are only beginning to understand. There is also dark energy, an even more mysterious component of the universe. Dark energy makes up approximately 68% of the total energy of the universe. It causes the expansion of space to accelerate, pushing galaxies apart ever more quickly. We do not know what dark energy is. It might be the energy of empty space itself, the so-called vacuum energy predicted by quantum mechanics. Or it might be something else entirely, a new field or force we have not yet discovered. Together, dark matter and dark energy make up approximately 95% of the universe. Ordinary matter, the stuff that makes up stars and planets and people, represents only about 5% of the total. We are made of a rare and precious substance, atoms, formed in the hearts of stars and scattered across space by supernova explosions, gathered together by gravity into planets where complexity can emerge and life can develop. This is the universe we inhabit, the observable region we can study and measure and understand. It is vast, it is ancient, it is filled with structures and phenomena that challenge our comprehension, and it is, quite possibly, just one small bubble in an infinitely larger multiverse, one region among countless others, each with its own history, its own structures, its own possibilities. Take a breath. Feel yourself present in this moment, this place, this tiny corner of the observable universe. You are here. That is enough. The universe continues around you, indifferent but not hostile, following its own mathematical laws, creating beauty and complexity through the blind operation of physical forces. Let us turn our attention now to spaces we cannot perceive directly, to dimensions that might exist but remain hidden from ordinary observation. This is the territory of string theory, a bold attempt to unify all the forces of nature into a single mathematical framework. In our everyday experience, space has 3 dimensions. You can move forward and backward, left and right, up and down. These 3 directions are independent, and any position in space can be specified by giving 3 numbers, 3 coordinates. Time is sometimes called a 4th dimension, though it behaves differently from spatial dimensions. Together, these 4 dimensions, 3 of space and 1 of time, constitute the space-time in which we live. But mathematics does not limit us to 4 dimensions. We can write equations in 5 dimensions, 6 dimensions, 1,000 dimensions. Whether these extra dimensions correspond to anything physically real is a separate question, one that can only be answered by observation and experiment. In the case of string theory, the mathematics strongly suggests that space-time must have more than 4 dimensions for the theory to work consistently. The simplest version of string theory, called bosonic string theory, requires 26 dimensions of space-time. More realistic versions that incorporate fermions, the particles that make up matter, require 10 dimensions. A more recent framework called M-theory, which attempts to unify the different versions of string theory, requires 11 dimensions. The immediate question is obvious. If space-time has 10 or 11 dimensions, where are they? Why do we only experience 4? The answer proposed by string theorists is compactification, an idea that goes back to early attempts to unify gravity and electromagnetism in the 1920s. The extra dimensions, according to this picture, are curled up into tiny spaces, far too small to be detected by current experiments. At every point in the 3 large spatial dimensions we experience, there is a small internal space of 6 or 7 extra dimensions, twisted and folded in complex geometric patterns. Imagine a garden hose viewed from far away. From a distance, the hose looks one-dimensional, appearing as a line. You can specify a position on the hose with just one number, the distance along its length. But if you zoom in, you see that the hose has thickness. There is a second dimension curled around the length of the hose, forming a circle at each point along the line. If that circular dimension is small enough compared to your distance from the hose, you will not notice it. The hose appears one-dimensional, even though it is actually two-dimensional. This is the basic idea of compactification. The extra dimensions are real, but they are curled up at each point in ordinary space, forming shapes so small that we cannot detect them. In string theory, these compactified dimensions are not simple circles, but incredibly intricate geometric structures called Calabi-Yau, manifolds, named after mathematicians Eugenio Calabi and Xingtung Yau. A Calabi-Yau manifold is a 6-dimensional space with special geometric properties that string theory requires. These manifolds can be extraordinarily complex, with elaborate topologies, holes and tunnels and surfaces wrapped around each other in ways that are impossible to visualize fully. The specific shape of the Calabi-Yau manifold at each point determines how strings can vibrate in those extra dimensions, and those vibration patterns determine the properties of particles and forces in the 4 large dimensions we observe. Different Calabi-Yau manifolds correspond to different physics. One shape might give rise to the particles and forces we actually observe. Another shape might give rise to completely different particles, different forces, a universe where chemistry works differently or not at all. The collection of all possible Calabi-Yau manifolds and the different physics they generate is called the string landscape, and it is vast. Early estimates suggested there might be around 10 to the power of 500 different possible configurations in the string landscape. More recent work suggests the number might be even larger or possibly infinite. Each configuration is a different possible universe, a different set of laws and constants, a different way for reality to be structured at the fundamental level. This presents both an opportunity and a problem. The opportunity is that the string landscape provides a natural explanation for why our universe has the particular laws it does. In the context of eternal inflation, different bubbles might settle into different configurations from the string landscape. We find ourselves in a bubble with the configuration that supports complex structure and life because that is the only kind of bubble where beings like us could exist. The problem is that with 10 to the power of 500 possible configurations, string theory appears to lose its predictive power. A good scientific theory should make precise predictions that can be tested by experiment. But if almost any conceivable set of physical laws can arise somewhere in the string landscape, then string theory predicts too much. It predicts everything and therefore, in a sense, predicts nothing. This has led to considerable debate within the physics community. Some researchers argue that the string landscape, combined with eternal inflation and anthropic reasoning, is the correct way to understand our universe. Others argue that this approach has led string theory astray, that a proper theory should explain why the constants have the specific values we observe, not just why those values are possible somewhere in a multiverse. Regardless of these debates, the mathematical structure of string theory itself is fascinating. The idea that reality might have more dimensions than we can directly perceive, that every point in ordinary space might contain hidden spaces with rich geometric structure, is profound. It suggests that what we think of as empty space is not empty at all, but filled with intricate structure at scales too small to observe. The size of these extra dimensions, if they exist, is constrained by experiments. If the compactified dimensions were large enough, we would see deviations from Newton's law of gravity at small distances. So far, experiments have found no such deviations, which means that if extra dimensions exist, they must be smaller than current experimental limits, typically around 1/10 of a millimeter at most, and possibly much, much smaller, down to the Planck scale, around 10 to the power of -35 meters. At the Planck scale, quantum effects of gravity become important. Space and time themselves become subject to quantum uncertainty, potentially breaking down into some more fundamental structure. String theory attempts to describe physics at this scale, where both quantum mechanics and gravity are important, something that conventional theories struggle to do. The Planck length, approximately 1.6 times 10 to the power of -35 meters, represents a fundamental scale where the smooth fabric of space-time might give way to a quantum foam, a churning uncertainty where the usual concepts of distance and duration become meaningless. In M-theory, the 11-dimensional framework that subsumes the different versions of string theory, there are not just strings but also higher dimensional objects called branes. A brane is similar to a membrane, a surface that can have various numbers of dimensions. A 1 brane is a string. A 2 brane is a surface. A 3 brane is a 3-dimensional volume, and so on. Some versions of brane cosmology suggest that our entire observable universe might be a 3 brane embedded in a higher dimensional space. The particles and forces we observe would be confined to this brane, unable to move in the extra dimensions, while gravity might be able to leak out into the higher dimensional space. This could explain why gravity is so much weaker than the other forces. most of the gravitational influence might be spreading out into dimensions we cannot access. These are speculative ideas, and it is important to be clear about what is established science and what is theoretical possibility. String theory has not yet been confirmed by experiment. No one has detected a compactified dimension or observed a string directly. The mathematical consistency and elegance of string theory are compelling to many physicists, but mathematics alone does not establish physical reality. Experiments do that, and so far, experiments have not provided direct evidence for strings or extra dimensions. Still, the possibility is there, hanging in the conceptual space of physics, a potential framework for understanding the deepest levels of reality. If string theory is correct, then the universe is even stranger than we typically imagine. Space is not just 4-dimensional, but 10 or 11-dimensional, with most of those dimensions hidden, folded away into geometric structures so small and so intricate that they remain beyond our current ability to probe. And if eternal inflation is also correct, then different regions of the multiverse might have different compactifications, different shapes for their hidden dimensions, leading to different physics, different types of particles and forces, different universes exploring different possibilities from the vast string landscape. What does this mean for you here now? It means that the space you occupy, the room around you, the air you breathe, every point in the world you experience might contain hidden geometric structure, dimensions curled up so small you will never perceive them directly, but nonetheless real, nonetheless part of the fundamental architecture of reality. It is a reminder of how limited our direct perception is. We see only a narrow slice of the electromagnetic spectrum. We feel only certain forces. We experience only 4 dimensions. And yet, beneath and beyond our experience, there may be layers of reality we can only glimpse through mathematics and inference, structures too small or too folded to be directly observed, but nonetheless present, shaping the behavior of everything we can observe. Rest with that thought. You exist in a reality that is deeper and more intricate than your senses can directly reveal. The world you experience is a projection, a low-dimensional shadow of something higher dimensional. And that something, whatever it is, follows mathematical laws we can partly understand, even if we cannot fully visualize the structures they describe. The universe is patient with our limited perception. It does not require that we understand it. It simply is, in all its hidden complexity, waiting to be discovered by those patient enough to work through the mathematics, clever enough to design experiments, curious enough to ask what lies beyond the visible. There is a mystery at the heart of quantum mechanics, one that has puzzled physicists for nearly a century. The mystery is why we perceive a definite, classical world when the fundamental laws of physics describe something quantum, something probabilistic and superposed and strange. Quantum mechanics tells us that particles do not have definite properties until measured. Before measurement, a particle exists in a superposition of all possible states. But when we look at the world around us, we see definite outcomes. The chair is here, not there. The cat is alive, not dead. The measurement device shows this value, not that value. How do we get from the fuzzy quantum world to the sharp classical world we experience? This transition is called the measurement problem, and there are several approaches to understanding it. One approach, which we have discussed, is the many worlds interpretation, which says that there is no transition. The quantum world remains quantum, but we perceive only one branch of a constantly splitting reality. Another approach is to posit that the wave function literally collapses when measured, transitioning from superposition to a definite state through some physical process we do not yet fully understand. But there is a third approach, called decoherence, which has become increasingly important in recent decades. Decoherence does not solve the measurement problem entirely, but it explains a crucial piece of it. It explains why large macroscopic objects appear classical even though they are ultimately made of quantum particles. The key insight of decoherence is that quantum systems do not exist in isolation. They interact constantly with their environment. Every atom in your body is colliding with other atoms, absorbing and emitting photons, exchanging energy with its surroundings. These interactions cause quantum information to leak out from the system into the environment, a process that destroys the coherence necessary for quantum interference effects to be observable. When a quantum system is in a superposition of two states, those states can interfere with each other, producing effects that have no classical analog. This interference is what makes quantum mechanics quantum. But when the system interacts with the environment, information about which state the system is in becomes encoded in the environment. The different branches of the superposition become entangled with different states of the environment, and these different environment states do not interfere with each other because the environment is huge and complex. This entanglement with the environment effectively divides the wave function into branches that evolve independently. From the perspective of an observer within one branch, the other branches are no longer accessible. They have decohered, separated by the spreading of quantum information into countless environmental degrees of freedom. Decoherence happens extraordinarily quickly for macroscopic objects. The larger the object, the more particles it contains, the more it interacts with its environment, and the faster decoherence occurs. For a dust particle floating in air, decoherence happens in less than a nanosecond. For a cat or a person, decoherence is effectively instantaneous. This is why we never observe macroscopic superpositions. By the time we could measure them, they have already decohered into classical-looking mixtures of states. But decoherence does not tell us what happens to the superposition. Does it actually collapse, with one branch becoming real and the others disappearing? Or do all branches continue to exist, as in the many worlds interpretation, just unable to interfere because of decoherence? This is where interpretations diverge. Decoherence explains why the world appears classical, but it does not fully resolve the measurement problem. What decoherence does provide is a mechanism for the emergence of classicality. It explains how the strange, counterintuitive quantum world at small scales gives rise to the familiar, deterministic classical world at large scales. The transition is not sharp or fundamental, but gradual and contingent on the system's interaction with its environment. This has practical implications for quantum computing. Quantum computers rely on maintaining quantum superpositions in systems large enough to perform useful calculations. But the larger the system, the more it interacts with the environment, and the faster decoherence destroys the delicate quantum states the computer needs to function. One of the major challenges in building quantum computers is isolating quantum systems from their environment long enough to perform calculations before decoherence turns them classical. In the context of the many worlds interpretation, decoherence is the mechanism that creates branches. When a quantum system decoheres, the different Branches of its wave function become entangled with different parts of the environment and evolve independently. From inside any one branch, the others are inaccessible, not because they do not exist, but because the entanglement with the environment has made interference impossible. This raises interesting questions about the nature of observation and consciousness. In older interpretations of quantum mechanics, consciousness played a special role, supposedly causing the wave function to collapse. But decoherence shows that no special role for consciousness is needed. Any interaction with a large environment is sufficient to produce decoherence. A measurement device decoheres whether or not a conscious observer looks at it. The results are recorded in the environment, in the microscopic states of particles and fields, long before any human becomes aware of them. This demystifies measurement to some extent. There is nothing magical about observation. What matters is interaction with the environment. Any process that entangles a quantum system with a large, complex environment will produce decoherence, making the system appear classical from the perspective of any observer within that environment. But this also means that decoherence is irreversible in practice, though not in principle. The quantum information that leaks into the environment is not destroyed, but it becomes spread out over so many degrees of freedom that recovering it would require controlling and reversing the dynamics of an astronomical number of particles. This is effectively impossible, which is why decoherence looks like an irreversible process, even though the underlying quantum mechanics is perfectly reversible. There is something peaceful in understanding decoherence. It demystifies the quantum to classical transition, showing that it arises naturally from the interaction of systems with their environment. You do not need consciousness or measurement or collapse to explain why the world looks classical. You just need interactions, entanglement, and the spreading of quantum information into environments too large to control. This is happening constantly, everywhere. Every photon that bounces off your skin and scatters into the room carries information about your position and state. Every air molecule that collides with you entangles with your quantum state. These interactions decohere you continuously, ensuring that you appear as a definite, classical object to yourself and others, even though you are fundamentally composed of quantum particles. The universe is constantly entangling with itself, dividing into branches that evolve independently, if the many worlds interpretation is correct, or collapsing into definite outcomes, if collapse theories are correct, or simply appearing classical through decoherence, if agnostic approaches are preferred. Regardless of interpretation, decoherence is a real, measurable, important process that shapes how quantum mechanics manifests at scales larger than atoms, and you are part of this process. Your very existence as a stable, macroscopic object is maintained by decoherence. Without it, you would be a quantum superposition, smeared out over countless possibilities, unable to have definite experiences or interact with the world in reliable ways. Decoherence is what allows coherent structures to persist, what allows the classical world to emerge from quantum foundations. Take a moment to appreciate this. You are a classical island in a quantum ocean, maintained by constant interaction with your environment, constantly decohering, constantly losing quantum coherence, and precisely because of this loss, able to exist as a definite entity with a definite history and a definite set of experiences. The universe maintains you through this process. It holds you together, gives you form and stability, allows you to be a person rather than a quantum smear. And it does this not through any intention or care, but simply through the impersonal operation of physical law, through the inevitable entanglement that occurs when quantum systems interact with large, complex environments. Rest in that knowledge. You are held together by the physics of the universe. Your definiteness, your solidity, your experience of being a single, continuous self all emerge from the interplay of quantum mechanics and environmental interaction. You are both quantum and classical, both wave and particle, both possibility and actuality, depending on the scale and the context in which you are viewed. Let us turn our attention now to a puzzle that has occupied physicists and philosophers for decades. A puzzle about why the universe has the particular properties that allow complex structures, stars and planets and life to exist. This is the puzzle of fine-tuning. The universe is described by a set of fundamental constants, numbers that appear in the equations of physics and determine the strength of forces, the masses of particles, the rate of cosmic expansion. These constants include the gravitational constant, which determines the strength of gravity, the electric charge of the electron, the masses of quarks, the cosmological constant, and many others. What physicists have noticed is that the values of these constants appear to be exquisitely calibrated to allow complexity to emerge. If gravity was significantly stronger, stars would burn out too quickly for life to develop. If gravity was significantly weaker, stars might not form at all, or might not produce the heavy elements necessary for chemistry. If the electric charge were different, atoms might be unstable, or molecules might not form. If the mass of the electron were different, chemistry as we know it would be impossible. The range of values for these constants that permit complexity is often very narrow. Change any one of them by more than a few percent, in many cases, and the universe becomes sterile, unable to produce anything interesting. This apparent fine-tuning demands explanation. One possible explanation is design. Perhaps the universe was intentionally created with these particular constants to allow life to emerge. This is a theological explanation, one that invokes a designer or creator. Some people find this explanation satisfying. Others find it scientifically unsatisfying because it does not generate testable predictions and seems to push the question back one level without truly answering it. Another possible explanation is that the constants are not free parameters, but are determined by some deeper theory we have not yet discovered. Perhaps there is a fundamental principle that constrains the constants to have the values they do, much as the laws of thermodynamics constrain how energy flows, or the principles of quantum mechanics constrain how particles behave. If this is true, then the apparent fine-tuning is an illusion. The constants could not have been different because they are fixed by deeper laws. But there is a third explanation, one that has gained traction in recent decades, particularly among cosmologists. This is the multiverse explanation, which says that the constants are not the same everywhere. In different regions of the multiverse, different bubbles from eternal inflation, or different branches of the quantum wave function, the constants take on different values. Most regions are sterile, unable to produce life. But in the tiny fraction of regions where the constants happen to fall within the narrow range that permits complexity, life emerges and observers arise who can notice and wonder about the constants. This is called the anthropic principle. The weak anthropic principle simply states that our observations are necessarily biased by the requirement that conditions be suitable for observers to exist. We should not be surprised to find ourselves in a region of the multiverse where the constants permit life, because we could only exist in such a region. The strong anthropic principle, a more controversial version, suggests that the universe must have properties that allow life to develop at some point in its history. The cosmological constant provides a striking example of apparent fine-tuning. Quantum field theory predicts that empty space should have energy, vacuum energy, arising from quantum fluctuations. When physicists calculate the expected value of this vacuum energy, they get a number that is approximately 120 orders of magnitude larger than the observed value. This is the worst prediction in the history of physics, off by a factor of 10 to the power of 120. And yet, the cosmological constant cannot be much larger than its observed value without catastrophic consequences. If it were significantly larger, space would expand so rapidly that galaxies could never form. Matter would be pulled apart before gravity could clump it into structures. The universe would be a cold, empty void, forever expanding, forever sterile. The cosmological constant must be extraordinarily small, fine-tuned to 1 part in 10 to the power of 120, to allow galaxies and stars and life to exist. Some physicists hoped that a deeper theory would explain why the cosmological constant is exactly 0. But observations in the late 1990s revealed that it is not 0. It is small but non-zero, just large enough to cause the expansion of the universe to accelerate, but small enough that galaxies had time to form before acceleration became dominant. In 1987, physicist Steven Weinberg made a prediction using anthropic reasoning. He argued that the cosmological constant could not be much larger than a certain value, or it would prevent galaxies from forming, making the universe lifeless. At the time, the cosmological constant was thought to be 0, but when it was finally measured in the late 1990s, the measured value fell within the range Weinberg had predicted using anthropic arguments. This lent support to the idea that anthropic reasoning might have real predictive power in a multiverse context. The fine-tuning of other constants is similarly striking. The ratio of the strong nuclear force to the electromagnetic force is approximately 137. If this ratio were different by more than a few percent, atomic nuclei would be unstable or would not form at all. The mass ratio of the proton to the electron is approximately 1,836. If this ratio were significantly different, chemistry would not work the way it does, and molecules necessary for life would not be stable. Even the spatial dimensionality of the universe appears fine-tuned. In 2 spatial dimensions, gravitational orbits are unstable. In 4 or more spatial dimensions, stable orbits are impossible. Only in 3 spatial dimensions can planets orbit stars in stable configurations for billions of years, providing time for life to evolve. The multiverse provides a framework for understanding this fine-tuning without invoking design or unlikely coincidence. If there are infinitely many universes with different constants, then the fact that we observe constants compatible with life is simply a selection effect. We exist in a universe with these particular constants because those are the only constants compatible with our existence. In universes with different constants, there are no observers to wonder about fine-tuning. This anthropic explanation is controversial. Some physicists find it deeply unsatisfying, arguing that science should explain why the constants have the values they do, not just why those values are possible somewhere. Others argue that the anthropic principle is a legitimate part of scientific reasoning, that recognizing selection effects is essential to avoiding false puzzles. What is clear is that the fine-tuning is real. The constants do appear to fall within narrow ranges that permit complexity. Whether this requires explanation through a multiverse, through deeper physical laws, or through design is a question that remains open, subject to ongoing debate and research. But for our purposes tonight, contemplating fine-tuning can be strangely comforting. The universe you inhabit is not random or arbitrary. It is structured in ways that permit order, complexity, beauty. The fact that you exist at all is evidence that you live in a universe fine-tuned for structure formation. You are not an accident or an anomaly. You are a natural consequence of a universe with properties that permit the emergence of complex, self-aware beings. Rest with that thought. The universe permits your existence. The constants are calibrated, whether by chance or necessity or design, to allow stars to shine, planets to form, chemistry to become complex, life to emerge, consciousness to develop. You are here because the universe is the way it is, and the universe is the way it is, at least in part, because that is the only way you could be here to observe it. Let us return now to the simplest version of the multiverse, the one that requires no speculative physics, only the straightforward assumption that space is infinite. This is the Level 1 multiverse in Max Tegmark's classification, and it has remarkable implications. If space is infinite and matter is distributed roughly uniformly on large scales, then every possible arrangement of particles within a finite volume must occur infinitely many times. This is a consequence of basic combinatorics. There are only so many ways to arrange a finite number of particles in a finite volume. That number is enormous, but it is finite. In an infinite universe, even enormous finite numbers are eventually exceeded. The volume within which particle arrangements are counted is called a Hubble volume, named after Edwin Hubble, who discovered the expansion of the universe. A Hubble volume is roughly the size of the observable universe, the region within which events can influence each other through light signals or other causal interactions. Beyond your Hubble volume, events are causally disconnected from you. They cannot affect you, and you cannot affect them. In an infinite universe, there are infinitely many Hubble volumes. Each one contains approximately 2 trillion galaxies, each with hundreds of billions of stars, each star potentially hosting planets. Most Hubble volumes will be different from ours, containing different galaxies in different configurations, different histories unfolding in different ways. But some Hubble volumes will be similar to ours, and some, at enormous distances, will be identical to ours. The distance to the nearest Hubble volume that is an exact duplicate of ours is truly incomprehensible. Physicists estimate this distance to be on the order of 10 to the power of 10 to the power of 115 meters. This is not a typo. It is 10 to the power of 10 to the power of 115, a number so large that writing it out in decimal notation would require more digits than there are particles in the observable universe. At this distance, there would be another Hubble volume with an exact copy of Earth, with an exact copy of you, reading or hearing these exact words, having these exact thoughts. The quantum states of every particle would be identical. The history would be identical. From your perspective and theirs, you would be indistinguishable. But this is only the nearest identical copy. In an infinite universe, there are infinitely many such copies, each separated by similarly incomprehensible distances. And between the identical copies, there are near identical copies, copies where one quantum measurement went differently, where you made a different choice, where history unfolded in a slightly different way. This has profound implications for questions of identity and uniqueness. In an infinite universe, you are not unique. There are other versions of you, identical or nearly identical, living out lives in distant Hubble volumes. But these copies are so far away, separated by such vast expanses of space, that they might as well not exist from your perspective. You will never communicate with them. You will never meet them. They are real, but they are forever beyond your causal horizon. Some philosophers find this disturbing, the idea that identity is not unique, that there are infinitely many copies of you scattered across infinite space. Others find it comforting, the idea that in some sense you are not alone, that variations of your existence are playing out in countless locations. Still, others remain skeptical that such reasoning is meaningful, arguing that infinitely distant copies have no bearing on questions of identity or existence. The Level 1 multiverse also implies that every possible outcome of every decision you make occurs somewhere. This is not because of quantum mechanics or parallel worlds, but simply because in infinite space, all possibilities are realized. In some distant Hubble volume, there is a version of Earth where you made a different choice, where history diverged at that moment, where your life unfolded differently. This is different from the many worlds interpretation of quantum mechanics, though the results are similar. In many worlds, the universe branches with every quantum event, creating parallel realities that exist in superposition. In the Level 1 multiverse, the different outcomes exist in different locations in ordinary space, separated by distances so vast that they can never interact. Both pictures suggest that all possibilities are realized somewhere in reality. Both offer a perspective where the specific outcomes you experience, while real and meaningful to you, represent only one thread in a much larger structure where all threads coexist. This perspective can be oddly liberating. The choices you make matter within your local context, within your Hubble volume, within the region of space-time you can influence. But in the larger context of an infinite universe, all choices are made, all paths are taken, all possibilities unfold somewhere. There is no single correct way for things to be. There is only the way things are here, in your location, in your moment, in your experience. The Level 1 multiverse is the least speculative type of multiverse. It requires only that space be infinite, a possibility entirely consistent with current observations. We do not know for certain that space is infinite. Measurements of the curvature of space suggest it is very close to flat, and a flat universe can be infinite, but the measurements are not precise enough to rule out slight positive or negative curvature, which would make the universe finite. If the universe is finite but very large, then the Level 1 multiverse does not exist. There would be only one Hubble volume, or at least only a finite number of them, and the infinite duplication of configurations would not occur. But if space is infinite, which is at least consistent with what we observe, then the Level 1 multiverse is real, and its implications are unavoidable. Somewhere, far beyond the reach of any telescope, beyond the cosmic horizon, beyond the limits of causal contact, there might be another you. They are living a life identical to yours or subtly different, making choices you made or different choices, experiencing joys and sorrows similar to or different from your own. They are as real as you are, as conscious as you are, as valid in their existence as you are in yours. And yet, from your perspective, they might as well not exist. You will never know them. You will never affect them. They are beyond your horizon, separated by distances so vast that even light, traveling for the entire age of the universe multiplied a billion times over, could not cross the gap between you. This is the strange reality of an infinite universe. Everything that can happen does happen, somewhere, somewhen. Every possibility is realized. Every configuration occurs. And yet, each location remains isolated, each Hubble volume evolving independently, each instance of awareness experiencing only its own local thread of reality. Take a breath. Let yourself feel present in this particular Hubble volume, this particular configuration of matter, this particular thread of possibility. You are here now, experiencing this moment. That is what matters. The infinite duplicates, if they exist, are beyond your horizon. This moment, this experience, this awareness is uniquely yours, even if identical moments are unfolding in infinitely many other locations. The universe is vast. The universe may be infinite. But you are here, in this place, in this moment, aware and present. And that is enough. We have explored several versions of the multiverse, each arising from different areas of physics, each with different levels of scientific support and different degrees of speculation. Now it is time to step back and consider the uncertainties, the debates, the questions that remain unresolved. The multiverse is not an established fact. It is a hypothesis, or rather a collection of hypotheses, each with varying degrees of theoretical motivation and empirical support. Some versions of the multiverse arise almost inevitably from well-tested theories. Others are more speculative, extrapolations beyond what we can currently observe or measure. The Level 1 multiverse, based on infinite space, is the least speculative. It requires only that space extends infinitely and that matter is distributed uniformly on large scales. Both assumptions are consistent with current observations, though neither is proven. We cannot measure whether space is infinite because we can only observe a finite region. We can measure curvature, and current measurements suggest the universe is very close to flat, which would be consistent with but does not prove infinite extent. The Level 2 multiverse, based on eternal inflation and the string landscape, is more speculative. Inflation itself is well supported by observations of the cosmic microwave background and large-scale structure. But eternal inflation, the idea that inflation continues forever, in some regions even as it ends in others, is an extension of inflation theory that has not been directly tested. And the string landscape, with its 10 to the power of 500 possible configurations, emerges from string theory, which itself has not been experimentally verified. The Level 3 multiverse, based on the many worlds interpretation of quantum mechanics, occupies an interesting middle ground. Quantum mechanics is the most precisely tested theory in physics, and the many worlds interpretation is a way of taking the mathematics of quantum mechanics seriously without adding extra assumptions about collapse or hidden variables. But whether the branches in many worlds are truly separate universes or just aspects of a single mathematical structure is a matter of interpretation, not observation. Critics of multiverse theories raise several concerns. One is the question of testability. Science, they argue, requires theories that make predictions which can be tested by experiment or observation. If other universes are forever beyond our ability to observe, then claims about their existence cannot be tested and therefore fall outside the domain of science. Proponents respond that the multiverse is not a theory itself, but a consequence of theories that can be tested. Inflation makes testable predictions about the cosmic microwave background. Quantum mechanics makes testable predictions about particle behavior. String theory, while not yet tested, is in principle testable and makes mathematical predictions about physics at high energies. The multiverse emerges from these theories as a side effect, not as an independent hypothesis. Another concern is the anthropic principle. Critics argue that anthropic reasoning is a retreat from the goal of science, which is to explain why the universe has the properties it does. If we simply say that the constants have their values because we could only exist in a universe where they do, we abandon the search for deeper explanations. We accept fine-tuning as brute fact rather than seeking underlying principles that determine the constants. Proponents respond that the anthropic principle does not preclude searching for deeper explanations. It simply acknowledges that some features of our observed universe might be explained by selection effects rather than fundamental laws. If the multiverse exists, and if different regions have different constants, then anthropic reasoning is not only legitimate but necessary to avoid false puzzles. A third concern is Occam's razor, the principle that simpler explanations are preferable to more complex ones. The multiverse, with its infinitude of unobservable universes, might seem like the opposite of a simple explanation. Why postulate infinitely many universes when one will do? But proponents argue that simplicity should be judged at the level of fundamental laws, not the number of entities those laws imply. The many worlds interpretation, for example, actually simplifies quantum mechanics by removing the collapse postulate. Eternal inflation arises naturally from inflation without adding new assumptions. In these cases, the multiverse is a consequence of simpler, more elegant theories, not an added complication. The debate over the multiverse touches on deep questions about the nature of science, the role of explanation, and the boundary between physics and philosophy. Is a theory scientific if it predicts unobservable entities? Can selection effects provide legitimate explanations? Should we accept implications of well-tested theories even when those implications are strange or counterintuitive? These questions do not have easy answers. Different scientists come to different conclusions based on their philosophical inclinations, their assessment of the evidence, and their intuitions about what makes a good scientific theory. What is clear is that the multiverse is taken seriously by a significant portion of the physics community. Papers about eternal inflation, the string landscape, and the many worlds interpretation appear regularly in peer-reviewed journals. Conferences are held, books are written. The multiverse is not fringe science, even if it remains controversial. But it is also clear that the multiverse has not been proven. We do not have direct evidence for other universes. We cannot point to observations that uniquely require a multiverse explanation. The case for the multiverse rests on theoretical arguments, on the implications of theories we have tested in other contexts, on the power of those theories to explain features of our universe that would otherwise seem arbitrary or fine-tuned. For someone encountering these ideas for the first time, it is important to hold the uncertainty lightly. The multiverse might be real. It might emerge from physics we already understand, or from deeper theories we have yet to discover. But it might also be an artifact of incomplete understanding, a theoretical possibility that does not correspond to physical reality. Science is a process, not a collection of fixed truths. Our understanding of the universe evolves as new evidence arrives and new theories are developed. The multiverse represents the current frontier of that understanding, a place where theory has run ahead of observation, where we are exploring possibilities based on mathematical consistency and theoretical elegance, waiting for experiments to catch up. This uncertainty is not a flaw. It is a feature of how science works. We push our theories as far as they will go, exploring their implications, making predictions, searching for ways to test them. Sometimes the theories are confirmed, sometimes they are refuted, sometimes they remain in limbo, neither proven nor disproven, waiting for better experiments or deeper insights. The multiverse is currently in that limbo state. It is a live possibility, taken seriously by serious scientists, but not yet established as fact. And that is okay. You do not need to believe in the multiverse to benefit from contemplating it. You can hold it as a possibility, a way of thinking about reality that expands your sense of what might be true, even if we cannot yet know for certain. Let yourself rest with that uncertainty. The universe is under no obligation to match your intuitions or preferences. It is what it is, following mathematical laws that unfold with beautiful indifference to human opinion. Whether the multiverse exists or not, whether reality is one universe or infinitely many, the fact remains that you exist, here, now, able to contemplate these questions and wonder at the strangeness of it all. We have journeyed through several versions of the multiverse, each offering a different perspective on the nature of reality. We have considered infinite space with its endless duplication of configurations. We have explored quantum branches where all possibilities coexist in superposition. We have imagined bubble universes spawning eternally from never-ending inflation. We have contemplated extra dimensions curled up smaller than atoms, hidden from direct view but shaping the physics we observe. Each of these pictures is vast beyond normal comprehension. Each suggests that reality is far larger, far stranger, far more intricate than everyday experience reveals. And each, in its own way, offers a kind of peace, a perspective from which the struggles and concerns of ordinary life can be seen in a different light. There is peace in vastness. When you contemplate scales of space and time that dwarf human existence, your own problems naturally shrink in proportion. The worry that keeps you awake at night, the decision you are struggling with, the relationship that troubles you, all of these remain real and important within your life. But they are also temporary, local, contained within one small corner of a universe, or multiverse, that extends far beyond your ability to influence or even observe. This is not nihilism. Your life matters. Your choices matter. Your experiences are real and valid. But they matter within a context, within a specific location in space and time, within a particular branch of possibility. And understanding that context can be oddly freeing. You are not responsible for the entire universe. You cannot control outcomes beyond your horizon. You can only act within your local domain, within the region you can influence, and that is enough. The multiverse, if it exists, is not watching you. It has no opinions about your choices. It does not judge or evaluate or care in any human sense. It simply is, following the mathematical laws that govern its behavior, creating and destroying structures across scales that range from the infinitesimal to the infinite. Within this vast, indifferent structure, you are a small, temporary pattern of organization. Matter and energy, arranged in a specific configuration that permits awareness, that generates experience, that asks questions about its own existence. You are, in a sense, the universe becoming aware of itself, one local instance of matter organized complexly enough to model its own behavior and wonder at the vastness in which it is embedded. This awareness is precious precisely because it is temporary and local. Consciousness arises from specific physical structures, brains made of neurons and synapses, patterns of electrical and chemical activity that give rise to thoughts and feelings and perceptions. When those structures dissolve, as they eventually must, that particular instance of awareness ceases. You will not continue forever. Your consciousness is tied to your physical form, dependent on it, unable to exist independently of it. But during the time you do exist, you have the extraordinary privilege of experiencing reality from within. You can see light that has traveled across billions of light years. You can understand equations that describe the behavior of particles and fields. You can contemplate scales of time and space that dwarf your own existence. You can hold in your mind, however imperfectly, the idea of a multiverse, a reality so vast that it contains everything that could possibly be. This is a gift, in a sense. Not a gift from anyone or anything in particular, but a gift of the universe's structure. The fact that matter can organize itself into patterns complex enough to be aware, to understand, to wonder. You did not ask to be born. You did not choose to exist. But here you are, conscious and present, able to experience the universe from your temporary perspective. How? You use this time, this awareness, this brief window of consciousness is up to you. The multiverse does not prescribe meaning or purpose. It does not tell you how to live or what to value. Those are questions you must answer for yourself within the context of your own life, your own values, your own understanding of what matters. But perhaps contemplating the multiverse can inform those answers. Perhaps understanding the vastness of reality can help you appreciate the preciousness of your local experience. Perhaps recognizing the countless possibilities that might exist in other branches or bubbles or Hubble volumes can help you embrace the specific possibility that is your life, here, now, in this universe, on this planet, in this moment. You are one configuration among infinitely many possible configurations, but you are the configuration that is here. You are the one having this experience, thinking these thoughts, feeling whatever you are feeling right now. That is not diminished by the existence of other possibilities. If anything, it is amplified, made more vivid by the recognition that this is your thread, your branch, your moment. The universe is not asking you to understand everything. It is not requiring that you hold in your mind the full structure of reality, which would be impossible anyway. It is simply unfolding, following its laws, creating and destroying patterns across all scales. And you are one of those patterns, temporary and local and aware, able to observe and contemplate and wonder. Let yourself rest in that knowledge. You are part of the universe. You are made of atoms forged in stars, organized through billions of years of evolution into a form capable of consciousness. You are, quite literally, the universe experiencing itself, knowing itself, marveling at its own existence. This is enough. You do not need to solve the mysteries of the multiverse. You do not need to understand quantum mechanics or string theory or eternal inflation. You can simply be here, present, aware, experiencing this moment as it unfolds. The universe will continue whether you understand it or not. Reality will persist whether you can explain it or not. Your role is not to comprehend everything, but to experience your small part of it, to live your life, to make your choices, to find meaning and beauty and connection within the limited scope available to you. The multiverse, vast and strange and possibly infinite, provides a backdrop against which your life unfolds. It is the stage on which your particular drama plays out, one story among countless others, all equally real, all equally valid. Your story is unique to you, even if similar stories are playing out in distant locations or alternate branches. This is your experience, your thread, your moment of awareness in the vast unfolding of reality. And that is enough. It has always been enough. The universe does not demand more from you than to exist, to experience, to be present. Everything else, all the meaning and purpose and value you find, you create within the context of your existence. You are the author of your own significance, within the constraints and possibilities provided by the universe you inhabit. Rest now. Breathe slowly. Feel yourself present in this moment, this place, this configuration of matter that is you. The multiverse, if it exists, will continue its vast unfolding without needing anything from you. And you can continue your smaller, local existence, making choices, forming connections, finding beauty and meaning in the limited scope available to conscious beings like yourself. You are here. That is the fundamental fact. Everything else, all the speculation about multiple worlds and eternal inflation and quantum branches, is interesting to contemplate, but does not change the basic reality of your existence. You are a pattern of matter and energy, temporarily organized into a form, capable of awareness, existing for a brief time in a vast cosmos or multiverse that extends far beyond your comprehension. And in this moment, that is enough. You exist, you are aware, you can rest, knowing that the universe is holding you, maintaining your structure through the operation of physical law, allowing you to persist for this brief interval before the pattern that is you dissolves back into the matter and energy from which it came. Sleep well. Dream peacefully. The multiverse, vast and strange, will still be there when you wake. We have reached the end of our journey through the multiverse, through infinite spaces and quantum branches and bubble universes and hidden dimensions. We have contemplated scales that dwarf comprehension and possibilities that challenge intuition. We have explored what science can tell us and where speculation begins. And through it all, we have returned again and again to the same basic truth. You are here, in this universe, in this moment, in this specific configuration of matter and awareness. The multiverse, if it exists, extends far beyond your horizon, containing possibilities you will never observe and cannot influence. But this moment, this experience, this thread of consciousness that is you, is real and valid and precious. Thank you for spending this time contemplating these ideas. Thank you for letting your mind expand to consider scales and concepts that are genuinely difficult to grasp. Thank you for sitting with uncertainty, for holding possibilities lightly, for recognizing that we are at the edge of what science can tell us about reality. If you found this exploration peaceful, if it helped quiet your mind, or offered a perspective that felt valuable, I invite you to subscribe to Nebula Nights. There are many more journeys like this one, explorations of galaxies and black holes and cosmic structures, all presented in this same calm, relaxed style designed to help you rest and wonder and drift peacefully towards sleep. Subscribing helps me continue creating this content, helps me explore new topics, helps me share the beauty and strangeness of the cosmos with others who, like you, find peace in contemplating the vast scales on which reality unfolds. If you feel moved to, Pressing the like button also helps this content reach others who might benefit from it. But more than anything, I hope you found something valuable here. I hope the multiverse, in whatever form it takes, offers you a sense of perspective, a reminder that your struggles and worries, while real and important to you, are also small and temporary in the context of vast space and deep time. I hope you can rest more easily, knowing that you are part of something incomprehensibly large, something that continues whether you understand it or not, something that holds you through the impersonal operation of physical law. The universe, or multiverse, asks nothing from you. It simply is, vast and patient, following mathematical rules that govern the behavior of matter and energy across all scales. And within this vast structure, you exist, briefly and locally, able to wonder and contemplate and experience the strange gift of consciousness. May you rest well. May your thoughts quiet. May you drift peacefully into sleep, held by the universe, part of its vast unfolding, one small thread in an infinitely large structure, real and valid and enough. Thank you for listening. Good night.